My name is Robert Boyd, and I'll be going over an AP Physics B question from 2007. The large container shown in the cross-section above is filled with a liquid of density 1.1 times 10 to the third kilograms per meters cubed. A small hole of area 2.5 times 10 to the negative 6 meters squared is open in the side of the container, a distance h below the liquid surface, which allows a stream of liquid to flow through the hole and into a beaker placed to the right of the container. At the same time, the liquid is also added to the container at an appropriate rate so that h remains constant. The amount of liquid collected in 2 minutes is 7.2 times 10 to the negative 4 meters cubed. Now, I've drawn this problem out. Here's our beaker, here's our container, and I've also listed all the givens in the problem. Let's start with part A. Calculate the volume flow rate of liquid from the hole in meters cubed per second. So it gives us the units. What our units need to be in. And now let's just think for a second. We know the volume of fluid that's exited the container, and we know the time that it did it in. By using those two, we can find our volume flow rate. So volume flow rate, which I'll write as a V with the dot on top, is equal to the volume exited, the time it did it in. Now, plugging in, 2 times 10 to the 4 meters cubed over 2 minutes, or 120, this needs to be in seconds, so 120 seconds. So plugging this in, we get 6 times 10 to 6 meters cubed per second. Perfect. Make sure you include your units. You could get points taken out for not doing that. Calculate the speed of the liquid as it exits from the hole. Now once again, let's ask ourselves, what do we have in the problem? We have the flow rate of the fluid leaving the hole, and we also have the area of the fluid leaving the hole. Let's try that. Say that volumetric flow rate is equal to our exit velocity, which I'll denote as such, times our area. Perfect. Now, resolving, we want our exit velocity. So resolving for our exit velocity, we have exit is equal to volumetric flow rate over our area. Plugging in, we have 6, 10, negative 6 meters cubed per second over 2.5 times 10 meters squared. Now, look at that. Our units are going to cancel out perfectly to give us meters per second. This gives us 2.4 meters per second. Great. Moving on to part C. Calculate the height of h of the liquid needed above the hole to cause the speed you determined in part B. So, what h of the liquid will give us this speed? Now, we can do this a couple of ways. We could use Bernoulli's theorem, which can relate the pressure, kinetic energy, and potential energy at one point, for example, the top, to another point, for example, the exit point. But a much quicker way to do it is using Torricelli's theorem. Torricelli's theorem relates this height h to the exit velocity through this hole. But in order to use Torricelli's theorem, you have to state it explicitly applies. So, let's write that. Torricelli's theorem applies. Right? Now, what is Torricelli's theorem? It's our exit velocity to our height, the square root of 2gh. Now, we have our exit velocity. Now we just need to find h. h equal to exit velocity squared over 2g. Exit velocity, let's just plug in 2.4 meters per second squared. Be careful with these units here. Over 2 times 9.8 meters per second squared. Now, that gives us h is equal to 0.2 meters. Perfect. Now, part D. Suppose that there is now less liquid in the container so that the height h is reduced to h over 2. In relation to the beaker, where will the liquid hit the tabletop? Now we only have 3 options for this answer. To the left of the beaker, in the beaker, or to the right of the beaker. And we also have to justify our answer. Let's think about this. Well, we know that if h is reduced to h over 2, but the pressure of this hole is now decreased. And by Bernoulli's theorem, if the pressure here is lower, then the velocity here is also going to be lower. That's one way, and we have to write that down. Or we could also look at Torricelli's theorem, which says that this exit velocity here will go down if this h goes down. So h reduces to h over 2, our exit velocity also goes down. So, doing all this, you would receive full credit on this problem. That's it. Thank you for your time.